we are almost finished with Simons. Okay, so recording has started. So is my screen visible? Screen, is it visible now?
Yes, sir. Now it's
Okay, okay, now it's visible. Okay, okay, great, great, great. Okay, so let us complete Simons, and then next week we will study some other topic. So okay, I just received a notification. So okay, let us. So just a quick recap. So in the morning we were looking at we completed Bernstein Wazirani, by the way, Qiskit implementation. And in the morning we looked at Simon's algorithm. We said that here also we have a task, just like Deutsch Jodsa, where we need to identify whether a function is 1 to 1 or 2 to 1. And we saw an important structure for the 2 to 1 function, which is x1 XORed with x2 is equal to s. That is the value of our string which we want to find with highest probability, and that can only happen when the coefficient is larger in value, right? So we saw that, and we also understand that dealing with amplitudes and maximizing some amplitude or minimizing some probability, these are all part of quantum interference, and we are consistently applying that. We already know what Hadamard gate does, what quantum parallelism is, it is superposition, etc. We already saw all those things, and with that we saw one important step in step 4 when we were doing our quantum circuit analysis. We saw in step 4 what is the derivation of the condition for 2 to 1 function, which is x1 XORed with x2 is equal to s. We saw the derivation for that, and I have mentioned you that if you do not understand the derivation fully, that's completely fine. You can just go through it, but it is the derivation for that condition of 2 to 1 function and how it comes about. So now, without worrying too much about that, and you can go through it, and like, and if you do not understand, that's completely fine. You can just revise it again, but the main thing is to understand that, like, what is the goal and what we are doing with Simon's algorithm, and where it is, like, what purpose we are using it for. So now let us so step 4. So we have completed 4 steps. So I would like to show the quantum circuit again. So if you can see, this is step 1, and then step 2, step 3, step 4. So only 2 steps are remaining, fifth and sixth. So now we are going to do step 5 and 6. So you can start writing from where we left off. So step 5 we can write, okay, step 5, okay, which is again applying Hadamard. And also I mentioned that this is also very similar to Deutsch-Jodza structure, applying Hadamard gates. So H gates, basically H gates to the first register, which will give you get 5 5, okay, which is 1 upon 2 to the n plus 1, and then summation z belonging to 0 1 n. Okay, then we have ket x plus ket y, right? So ket x, ket y, if you see here, 5 4. So therefore on both of them Hadamard will apply, right? So directly again refer back to the formula which I have mentioned last week when I was teaching you Deutsch and Deutsch Jodza, how these are coming, x dot z, y dot z. I will not explain how this is coming. This is coming from directly from that formula which I taught you last week. Okay, so then we have the variable ket z, as you already know, and that is it. That is steps 5. Okay, now last step. Okay, step 6. Step 6 is about what? Step 6 is about measurement, right? Last step, measuring. Okay, so measuring, we are going to measuring the first register. Okay, again second we don't do anything, will give an output only if, okay, so measuring the only if when -1, so this is the condition of the output, x dot z becomes equal to -1 y dot z. And that makes sense also because, like, we have two terms, and if they equal each other, then only the amplitude value is going to increase, right? If they are not equal, then it's not going to increase. So which means that x dot z is equal to y dot z, and that means x dot z is equal to y. We already know x XOR s, we have already seen this, right? Dot z, right? In step 4 we saw in the today morning only, 10 to 12 class, right? We have seen this. X dot z is equal to x dot z, just like, you take that, like, just multiply z with x and s dot z, and then therefore s dot z will be equal to s dot it should be 0 mod 2. So what does this mean? Let us understand what does this means. Okay, what will happen. Okay, and when we are solving, so this is the last step. So again, like, when we are solving this quantum algorithm for Simon, it is directly going to give us the string. So a string, we don't have to do any extra calculation, as I have mentioned in the Simon's algorithm process. So a string, but I will write it for just sake of completion. A string z will be measured whose inner product with s is equal to 0, whose inner product is with s is equal to 0, thus repeating the algorithm about n times, we will be able to obtain we will be able to obtain what? N different values. Okay, n different values of z, and the following system of equations can be written. So if you remember, like I told you that you have to later solve, and we have kept that for period finding. Okay, we are not going to use that for secret string. So this is, I am just writing that for sake of completion. So you will have these expressions as 2 0 and like that, so on. Okay, s dot zn is equal to 0, and s can be determined by Gaussian elimination, right? Gaussian elimination, which is like a way of solving multiple linear equations, right? So that's it. That is the end of step 6, just measurement, and we get the result. And now what happens? So let me write a few points. So this is like, the analysis is complete here. So let us write a few points. So we only get a unique non-zero solution is if we are lucky. Then second point is the probability that z1 z2, okay, up to zn are linearly independent, okay, linearly what independent is at least what is the probability, this it is given by, you do not need to remember these points, this is for the completion of the algorithms I'm writing, okay, just for your extra information. 1 minus 1 divided by 2 to the k, okay, which is almost equivalent to 0.2888, and which is greater than 1 by 4, okay, it is greater than 1 by 4, this value. Now, and the last point, and then we will see Qiskit implementation, and that's it. Simon's algorithm is finished. Okay. If we run, if we run the algorithm, if we run the algorithm 3n times, the probability, okay, the probability that we will obtain n linearly independent equations, okay, linearly independent equations is at least 2 by 3. So it's basically at least 2 by 3 means greater than 2 by 3. That means almost like, nearing 100% probability that you will definitely get about n linearly independent equations, and from that you can derive the string. And this is for the case when the string is very, it can be very large, right? I mean, we are going to try a very simple string now, okay, that's nothing, right? I mean, we will simply try for 2 qubits, okay, where, like, in Simon's, as you already know, second register also has the same number of qubits as the first register, right? So if there are n qubits in first register, second qubit also has the equal number of qubits, so it will also be n, right? We have already seen that, right? So it is n qubits, right? It is a n qubits here, okay, n qubits here. We have seen this in the morning, right? Okay, so this completes, so basically this completes your derivation of the Simon's algorithm with a few points. And now let us see the experimental nature of Simon's algorithm. Okay, so this is the experiment with Python, which is done for Simon's algorithm with Qiskit, as you see. And again, the code is very easy, it's not very hard, you can easily understand what we are doing. And as you can see, like, we have imported these libraries, right? Qiskit and quantum circuit, etc., you already know that, and we are going to plot the histogram, okay, to check whether we are able to find our hidden string or not. And that's the problem which we are focusing on, right? So now what happens is we decide our secret string s, okay, and we make it 1. We create registers, okay. One is the input qubit, and then total qubit, okay, which is 2 times the input qubit, okay. So that will be the total number of qubits. So we create our quantum circuit with total qubits, basically twice of the input size, okay. And then we give the second argument as input qubits. Why is that? The reason, because second argument deals with the classical bits, right? and we will require only that much number of classical bits which which we will measure from the first register. Since the first register has n qubits, okay, which is equal to the size of the string, okay, that is what we have seen, right? This is equal to the size of the string. Therefore it is valid to have input qubits this value in place of this classical, because classical register will only be measuring the first register, not the second one. Second one also has n qubits, right? But we are not going to measure it as we have seen in the algorithm. This is very same as Bernstein, Vazirian, Deutsch and Deutsch Jodza, right? So similar kind of structure. So very easy to understand this code. And then we apply Hadamard gate, right? So we apply Hadamard gate to all the input qubits. We put a barrier, and then what we do is that we create our oracle function. Again, this is also very easy. Okay, but this time what we are doing with the oracle function is that this time we are going to, since there is a one present in the secret string is 1 0, right? So therefore only the first qubit will have the control, second qubit will not have any control, and the targets will be one by one given to the second register qubits. Okay, so what I'm trying to say is this. So since it is 1 0, okay, it starts with what, 1 0, right? Since it starts with 1 0, therefore what we do is that we take only that control which is 1, okay, and we put controls one by one to the second register qubit. So q2 q3 are second register qubit, same number as that of the first register. First register is q0 q1, right, 2 qubits, and same number as in the second register, which is q2 q3, right? So we put that because this is 1, okay, 1 0. If it was 0 1, what would have happened? Then this control would have been here, right, in the second qubit. It was, if it was 0 1, okay. So therefore what happens is that whenever you take these kinds of string and then whenever you apply this, then this is the oracle for this part. And now what is going to happen is that you are going to execute this, and once you execute this you get this kind of result, 0 0 and 0 1. So what is the meaning of this? Okay, so as we can see from this that we have 0 0 and 0 1, and 0 1 is our secret string also. Okay, uh, secret string is 1 0 basically, so this is just reverse, so you already know that. If we had only 0 0 as the result, then this would have mean that the f is a one-to-one function, but you can see it is not only a 0 0 result. The result is split it up. Okay, the result is split, right? And if you recall, in the first register, after measuring the second register was collapsed, right? We were getting a superposition of ket x plus ket y. Okay, we were getting two states, if you recall, ket x plus ket y. So that also proves, okay, so from theoretically and practically also you can connect it, right? It's easy to connect that. Okay, yeah, indeed we get, like, you can connect in your mind that, okay, like, in step 4 we took the measurement, but then we received the superposition state. Okay, so therefore in the output there should be some sort of superposition, and we can see that yes, it is indeed a superposition state which we are getting, where everything is occurring 50-50% time. Okay, so this would have been possible if AC is equal to 0 0. Since we have AC is equal to 1 0, so therefore that is the thing. Okay, 2 to 1 function. Okay, and you can also try with 0 1 1 1. Please go ahead and, like, try all those experiments. Okay, that is for your own knowledge. Okay, so do try them whenever these notebooks are shared with you, because that enhances your understanding of, like, and maybe you should also try with what happens if you have 3 qubits. Okay, make the circuit larger. Okay, what will happen if you have 4 qubits? In 4 qubits you have more possibilities of having ones, right? 1 1 0 0 0 0 0 1 1, then 1 0 1 0 0 1 0 1, so many possibilities, right, in 4 qubits. So do these kinds of interesting experiments to get more out of your curriculum and everything. So that is what you should do. And then this is nothing. This is that's it. So Simon's algorithm is complete till this part. This is just some extra code. Okay, if you would like to print the unitary matrix for the secret string, basically this is the, like, this is our unitary. So if you would like to plot it, like what will be the unitary matrix of that 4 qubit thing. So you will get like, since it is 4 qubit, therefore how much what will be the size? 16 cross 16, right? 2 to the 4. Okay, 16 cross 16. So this is the 16 cross 16 matrix, that's why it looks so large, right? So again, I mean, this is optional. You already know what is a unitary simulator, so you can do it for anything if you like. This is just optional step. And then again, like, if you want to obtain a state of a quantum circuit at a particular instant, you can put a barrier and, like, measure there with the state vector simulator and print that. So I mean, these operations you already know that. This is just some extra information, you can consider them as revision. Okay, so this is what it is. Okay, this is Simon's algorithm, and very all these four algorithm, Deutsch, Georgia, Bernstein, Vazirian, and Simons. These four are very interconnected, right? But now after this, we are going to diverge away from this interconnectedness of topics, and we are going to explore some other topics. Okay, we are going to learn quantum Fourier transform. Okay, we are going to learn quantum phase estimation, right? Quantum phase estimation utilizes quantum Fourier transform. Then you are going to learn Shor's algorithm, which utilizes quantum phase estimation. So this QFT, QPE, quantum phase estimation, QFT, quantum Fourier transform, and Shor's algorithm, very interconnected. So if you learn QFT, you should be able to understand QPE. And then if you have learned QPE, then you can use it for Shor's algorithm. Okay, so this is how, like, things are connected. And these three algorithms will be definitely covered in advanced cards, and after that we will see some basic concepts of variational quantum algorithm. But before the course finishes, so before basic course finishes, there will also be lectures on quantum key distribution and some very basics on quantum computational complexity. So with that, quantum computational complexity will not be too large. Maybe it will be just a few minutes only, just some very basic introduction. And then QKD will be there, and QKD will be taught, and QKD uh, will be practically demonstrated using Qiskit. So very similar, like, quantum teleportation and super dense coding, quantum communication protocols, they are cryptography. And similarly, QKD will be a quantum cryptography protocol, which you will be seeing. Okay, so for the quantum algorithms part, I think this is it for the basic course. This finishes that quantum algorithm. Next is not quantum algorithm, but QKD protocol, just like you have learned teleportation and superdense. Then after that, again, we will come back to quantum Fourier transform and QPE, quantum phase estimation, etc. Okay, so this concludes this lecture. I will stop the recording